Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here.
This is Andrew and Renee. Welcome to the SAC series.
Today we are exploring warp drives and the physics of faster-than-light travel.
It really is the ultimate dream of spaceflight, isn't it?
Yeah.
I mean, it's the holy grail of propulsion.
Oh, absolutely. I think for anyone who grew up watching Star Trek or even something more modern like Interstellar, it's baked into our cultural DNA. You see the captain say, engage, the stars streak into these long lines, and suddenly you're halfway across the galaxy in time for dinner.
It just changes the whole scale of the universe.
It does. It's the difference between space travel being this multi-generational, slog where you and your children and your grandchildren die before you even get to the destination, and it being an actual adventure. It turns the universe from a vast, lonely graveyard into a neighborhood you can actually visit.
That's a great way of putting it. It's the difference between trying to cross the ocean on a little raft versus hopping on a supersonic jet. On the raft, the journey is the entire life of the traveler.
Right.
On the jet, the journey is just a commute. But in the real world, as opposed to the writer's room at Paramount, we run into a very, very stubborn traffic cop.
And his name is Albert Einstein.
Exactly.
Right. The universal speed limit, Physics 101, nothing with mass travels faster than light. That number, C, is. It's not just a good idea, it's the law.
It is the law.
So usually when we talk about this, we are strictly in the realm of science fiction. But today, looking at the stack of papers we've got in front of us, we aren't.
Not entirely, no. Today we're moving from pure science fiction into a field that's actually called metric engineering.
Metric engineering.
Yes. And we aren't just talking about dreams anymore. We're talking about peer-reviewed solutions to Einstein's own field equations. We have a whole stack here. From the seminal 1994 breakthrough by a physicist named Miguel Alcubierre, all the way up to research published as recently as 2025 by Kiao and others.
So these are serious physicists taking this seriously.
Very seriously. They're looking at the math that suggests this might just be possible, and also, to be fair, the physics that screams that it probably isn't.
So the mission for our conversation today is to really unpack that. Can we actually build a starship that surfs on a wave of spacetime? Or are there fundamental laws, things like energy conditions or causality, that are going to keep us grounded in our own solar system forever?
That is exactly the question. And to get anywhere near an answer, we have to start at the foundation. We have to go back to 1994 to Miguel Alcubierre.
Okay, let's get into it. Because before 1994, the consensus was pretty much FTL is impossible, end of story. Special relativity is a harsh mistress. So what did Alcubierre see that everyone else had missed?
Well, the genius of it was that he didn't try to break the speed limit. He found a loophole.
A loophole in general relativity.
Exactly. You see, special relativity is what tells you an object with mass, that you cannot move through space faster than light.
Right. As you get faster, your mass increases, you need more energy, and at the speed of light, you'd need infinite energy. It's a wall.
It's a mathematical and physical dead end.
Yeah.
The equations just blow up. But general relativity, that's a different beast. It describes the behavior of spacetime itself. And there is absolutely no rule in general relativity that says space cannot expand or contract faster than light.
And we know it can, right? The Big Bang.
Inflation.
Precisely. Inflation theory suggests that in the very first moments of the universe, it expanded at a rate that was orders of magnitude faster than the speed of light. Space itself was ballooning outwards.
So Alcubierre's big idea was, if space can do it on a cosmic scale, why can't I make a little local patch of space do it for me?
That's the core of it, yes. He wrote down what we now call the Alcubierre Drive, or more formally, the Alcubierre metric. And a metric, just so we're all on the same page, in this context, is what?
A metric is, it's essentially the mathematical function that defines the geometry of space-time. It's the rule book that tells you how to measure distances and time in a universe that might be curved by gravity. So Alcubierre just wrote down a new rule book for a very specific situation.
Okay, so paint me the picture. I'm in my spaceship, I flip a switch and turn this thing on. What happens to the space around me?
Imagine your ship is just sitting there, inside a perfectly flat, normal bubble of space-time. Inside that bubble, everything is calm. The laws of physics are just as you know them.
So far, so good.
But the drive mechanism, whatever it is, acts on the geometry outside the walls of that bubble.
Yeah.
And it does two things simultaneously. It violently contracts the space in front of the ship.
So if I'm looking at a star that's 10 light years away, the drive effectively crumples up that 10 light years of distance. It reels it in like a fishing line.
It pulls the destination closer to you, yes. And at the exact same time, it does the opposite behind you. It expands the space behind the ship.
So it's pushing my starting point further and further away.
Yes. And the classic analogy, which is really the best one, is a surfer on a wave. The surfer might not be paddling very fast relative to the water right next to their board.
Yeah, they might just be standing still on the board.
Right. But the wave itself is moving, and it carries the surfer forward at great speed. In this case, the ship isn't moving through space. It's being carried by a moving wave of space.
I really want to drill down on that because that is the part that bends my brain every time. If I'm standing on the bridge of this starship and we are moving at, let's say, 10 times the speed of light warp 2 or whatever you want to call it, what does my speedometer actually say?
If that speedometer is measuring your speed relative to the space immediately surrounding you, inside that bubble, it reads 0.
A 0.
You are at rest. Locally, you are not moving. And that is absolutely crucial.
And here's where it gets really incredible for any passengers on board. Because you'd think that accelerating to 1,000 times the speed of light in a few seconds would turn a human being into, well, jelly. The G-forces would be insane.
In a normal rocket, absolutely. That's inertia. You push the rocket pushes you back. But remember, inside the Alcubierre bubble, space is flat. You are in what's called free fall. You feel completely weightless.
So I could be sipping a cup of hot tea while the universe is whizzing by at superluminal speeds, and I wouldn't spill a single drop.
You wouldn't even know you were moving, other than looking out the window. Because the ship isn't pushing against you. The patch of space that you are occupying is what's moving.
It's the old tablecloth trick.
It is the ultimate tablecloth trick of physics. The universe is the tablecloth. The ship and its contents are the dishes. And Alcubierre found a theoretical way to pull the tablecloth without disturbing any of the dishes.
It sounds way too good to be true. It solves the speed limit, it solves the G-force problem, and it solves the time dilation problem too, right? Because inside the bubble, time just flows normally.
That's right. In special relativity, the faster you go, the slower time ticks for you. That's the whole twin paradox thing.
Right. You fly off near light speed, you come back, and your twin is an old man.
With the Alcubierre Drive, since you are locally at rest, there's no time dilation. The clock on the ship and the clock back at mission control stay perfectly synchronized.
Okay, so we have a magic carpet that doesn't spill our drinks and keeps us young. There has to be a catch. Physics never, ever gives out free lunches.
And this is a massive catch. I mean, a catch that could be the size of the entire universe. It all comes down to the energy problem.
I figured we'd need a lot of batteries.
It's not just the amount of energy, though that is a problem. It's the type of energy. And to understand that, we have to talk about something called the weak energy condition.
All right, let's break that down. What is the weak energy condition, or WEC?
In classical general relativity, it's a fundamental assumption. It basically says that any observer anywhere in the universe will always measure the energy density of matter to be non-negative.
Meaning mass is positive, energy is positive, things have weight.
Right. And gravity is attractive. You put a planet in space, it pulls things toward it, it creates a gravity well, bending space-time down like a bowling ball on a trampoline.
That's gravity as we all know it.
But think about what the Alcubierre Drive has to do. To contract space in front, that's normal gravity, that's attractive. You could do that with positive mass and energy. But to expand space behind you,
you need the opposite of gravity. You need a repulsive force.
You need anti-gravity, in a sense. You need the geometry of space-time to curve the other way, to bend up instead of down. And to achieve that expansion behind the ship, the Alcubierre metric requires the energy density to be negative.
Negative energy, which, to my ears, sounds like magic or unobtainium from the movie Avatar. Does this stuff actually exist, or is it just a minus sign on a piece of paper that a theorist wrote down?
That is the multi-billion-dollar question. Classical physics, the physics of our everyday world, says no way. It directly violates the weak energy condition. But when we bring quantum mechanics into the room, things get a little bit fuzzy. We actually do see tantalizing hints of negative energy in quantum field theory.
You're talking about the Casimir effect.
I am. It's really the standard proof of concept that people point to for negative energy. If you take two perfectly smooth, uncharged, conductive metal plates and you place them extremely close together in a perfect vacuum, we're talking microns apart, something very strange happens.
They get pushed together.
They do. And the reason is fascinating. The quantum vacuum isn't empty. It's seething with virtual particles, pairs of particles and antiparticles that pop into existence and annihilate each other almost instantly.
It's a sort of quantum foam.
A quantum foam, exactly. And these fluctuations behave like waves. Outside the two plates, waves of all possible sizes and frequencies can exist. But between the plates, only waves that fit perfectly in that tiny gap can exist. The longer wavelengths are excluded.
Like plucking a guitar string. You can only play the notes that are allowed by the length of the string between the fret and the bridge.
Perfect analogy.
Yeah.
So there are fewer modes of these virtual waves between the plates than there are outside. This means there is more quantum pressure pushing in from the outside than there is pushing out from the inside.
And that's what pushes the plates together. So where's the negative energy in all this?
Well, because there are fewer vacuum fluctuations inside that gap, the energy density between the plates is measurably lower than the zero-point energy of the vacuum outside. If we define the energy of the empty vacuum as zero, then the space between the plates has a negative energy density relative to that vacuum.
Okay, so it's real. Negative energy is a real physical phenomenon we can create and measure in a lab with two metal plates. It's not just a math trick.
We can, but, and this is the crucial part, the scale is the issue. We're talking about incredibly tiny amounts of energy over microscopic distances. The Alcubierre Drive requires this negative energy to be smeared out over a massive region, the entire wall of a bubble surrounding a spaceship.
And this is where we get to the first major hurdle that popped up right after Alcubierre published his paper. It's the, okay, so how much fuel do we actually need question. And a couple of physicists, Fenning and Ford, ran the numbers.
They did. They took the Alcubierre metric, they applied the known constraints of quantum mechanics, and they calculated the total energy required for a bubble that was about 100 meters across. So, roughly the size of a decent starship.
Give it to me straight. How bad was it?
According to their first calculations, using the original unoptimized Alcubierre geometry to sustain that bubble, you would need an amount of negative energy equivalent to negative 10 times the mass of the entire observable universe.
I'm sorry, did you say negative 10 universes?
Roughly, yes.
Okay, that's discouraging. That's not a case of we need a bigger reactor. That's a case of the fundamental laws of physics are openly laughing at us.
It was a massive blow. It basically made the entire concept seem completely unfeasible. It implied that to generate the required curvature, the wall of the bubble had to be so incredibly thin that the energy density inside it would spike to infinity.
So case closed. Did everyone just pack up and go home?
Not quite. And that's the beauty of theoretical physics. It's a negotiation. You say it costs 10 universes, and the next person says, well, hang on, let me check the geometry again. And in 1999, a physicist named Chris van den Broek came along and proposed a modification.
He optimized the bubble's shape.
He did. He realized that the geometry didn't have to be a simple sphere. He proposed a much more complex shape, one that involves a very, very small neck connecting the interior of the bubble to the outside world.
Wait, describe that for me.
Imagine a bottle. The neck of the bottle is microscopically small, maybe just a few Planck lengths wide. But the body of the bottle, the inside, is huge. The spaceship sits comfortably inside the main body of the bottle.
It's like the TARDIS from Doctor Who. It's bigger on the inside.
Geometrically, yes, that's the idea. Van den Broek showed that you could keep the interior volume large enough for a ship and crew, but you could shrink the surface area of the bubble, the part that actually interacts with the outside universe and requires all that negative energy down to a microscopic size.
That's very clever. You minimize the surface area to minimize the fuel cost.
Exactly. And the numbers, well, they just dropped precipitously. He found that by optimizing the shape in this way, you could reduce the total energy requirement from 10 universes all the way down to something like a few solar masses.
Okay, now a few suns is still an unbelievable amount of energy. I don't have a few suns sitting in my garage.
Okay.
But it is a heck of an improvement over 10 universes.
It is.
We're moving from the realm of cosmically impossible to just incredibly mind-bogglingly difficult.
It's progress. And later work pushed that number down even further to maybe the mass of Jupiter or even the mass of the Voyager spacecraft. But the fundamental problem was still there. Even if it's only the mass of Jupiter, it has to be negative mass. We still need that exotic matter, and we still don't have any idea how to produce it in bulk.
And this really leads us into the second phase of this whole story, the active debate, doesn't it? Because there's a whole camp of scientists, very smart, very rigorous people who argue that even if you could somehow get the energy, nature has built-in safeguards to stop you from ever using it.
Right.
That the universe basically has an immune system against things like warp drives.
Correct. This is where we get into what are often called the unphysical arguments.
Yeah.
And the primary weapon that skeptics use against the warp drive here is something called quantum inequalities, or QI.
This was developed by those same two guys, Ford and Roman, right? I was reading about this in our stack. They use the bank loan analogy. I love this analogy because it makes quantum mechanics feel, I don't know, relatable.
It's a fantastic way to think about it. The quantum inequalities suggest that nature operates like a very strict, very predatory bank. You can borrow negative energy from the vacuum. You can take out a loan, like we see in the Casimir effect. But the bank has some very strict rules.
Rule number one, you always have to pay it back.
Yes. You can never sustain a negative energy state indefinitely. You must eventually repay that energy debt with an equal or greater pulse of positive energy.
And then there's rule number two, the interest rate.
The quantum interest. And the rates are astronomical. The fundamental rule is this. The more negative energy you borrow, the deeper your energy deficit, the shorter the amount of time you're allowed to keep it.
So if I only need a tiny little bit of negative energy, I can maybe hold on to it for a little while. But if I need a massive amount to warp the fabric of space-time.
The bank says, fine, take it, but you have to pay it back in a fraction of a nanosecond.
Which is a bit of a problem if you're trying to fly to Alpha Centauri. I mean, you need the bubble to last for years, not picoseconds.
Exactly. So Fenning went back and applied these quantum inequalities to the warp drive. And he found that to get around the interest limits, the wall of the warp bubble, that shell where all the negative energy lives, would have to be impossibly thin to sort of trick the vacuum.
How thin are we talking?
We are talking about something on the order of 100 Planck lengths.
And for context, a Planck length it's absurdly small.
It is the smallest meaningful unit of length in all of physics. It's about 1033 meters. It is to a single atom what that atom is to our entire solar system.
Wow.
A wall that thin is just physically unrealizable. If you try to confine that much energy into a space, that small quantum gravity effects would completely take over and the whole thing would break down. So the conclusion from this camp is that any macroscopic warp bubble is fundamentally unstable. You'd turn the engine on and the bank would immediately foreclose on your energy loan before you'd moved an inch. The bubble would just collapse.
That feels like a pretty definitive shutdown. Just access denied by the laws of quantum mechanics. But the skeptics didn't even stop there. We also have the horizon problem, which sounds less like a bank loan and more like a pure logistical nightmare.
It's a control problem.
Yeah.
And it stems directly from the very nature of faster-than-light travel. If you are moving faster than light, then by definition you are outrunning your own light cones.
Okay, let's break that down. Light cone.
A light cone is a concept from relativity. It represents the path that light, and therefore any causal influence, can take from a single event. Nothing you do can affect anything outside your future light cone. Now, imagine the warp bubble is moving at, say, 10 times the speed of light.
Okay.
The front of that bubble, the leading edge where space is being contracted, is moving forward faster than any signal you can possibly send from the cockpit.
So I'm the captain. I see a giant asteroid right in our path. I slam on the brakes.
The signal from your brake pedal travels at the speed of light. But the front of your bubble is moving at 10 times the speed of light. Your stock signal never ever catches up to the engine. You are causally disconnected from the front of your own ship.
So I'm essentially flying blind, and I can't steer or stop. That's the captain's dilemma.
It's even worse than that. A physicist named Sergei Krasnikov pointed this out. He argued that a ship cannot even create the path in front of it. The signal to tell space-time to warp now would have to travel superluminally just to get ahead of the ship to lay the track.
It's like you're trying to lay down train tracks while the train is already moving at full speed, but your track-laying machine is slower than the train.
Precisely. You will always run out of track.
So did Krasnikov's objection just kill the warp drive concept entirely?
No, he just changed the required infrastructure. He proposed what are now famously called Krasnikov tubes.
The superluminal subways.
That's the idea. Imagine you have to build a tube of distorted space-time in advance. So you take a ship, and you travel at normal sublight speed to your destination, say Alpha Centauri. And as you go, you lay this track. You permanently distort the space-time along your path.
So the first trip is the slow boat. It takes you 4.3 years just to get there.
Right. But once that tube is built, the space-time inside it is permanently warped in such a way that it allows for faster-than-light travel back along the path you just created.
So the first trip out is slow, but the commute back home is instantaneous.
Effectively, yes. And any subsequent ships can then zip back and forth through this pre-built subway tunnel. It's like building the Transcontinental Railroad. The first crew has to walk the whole way hammering spikes, but once it's done, the express train can run.
That feels a little more grounded in a weird way. It's a huge infrastructure project for the first trip, but it allows you to build a network. It does kind of defeat the Star Trek fantasy of let's boldly go see what's over there right now.
It does. You can only warp to places you've already been. So it would restrict initial exploration to sublight speeds, but it would allow for incredible FTL trade and communication within an established interstellar civilization.
And then just to pile on even more bad news, there's the heat problem. I saw this mentioned in a few of the papers, this idea of an entropy warp limit.
This is where thermodynamics gets a seat at the table. Warping space-time isn't a free action. It's an information processing operation you're performing on the quantum vacuum. You are forcing it into a highly ordered state that decreases entropy locally.
Which means you must increase entropy somewhere else, and that means heat.
Massive amounts of heat. Specifically Hawking radiation, the same kind of thermal radiation that's predicted to come off the event horizon of a black hole, would be generated at the horizon of the warp bubble.
And since the bubble completely surrounds the ship,
that radiation has nowhere to go but in. Some of the calculations suggest that for a bubble moving at any significant FTL speed, the interior temperature would skyrocket to millions of degrees almost instantly.
so we arrive at Alpha Centauri in record time, but we arrive as a cloud of superheated plasma.
You'd be cooked to a crisp. Or, the alternative to avoid that is to make the walls of the bubble so incredibly thick that the Hawking radiation is manageable, but then you're right back to requiring the energy of the entire universe to sustain it.
It really feels like the physics community was just playing a game of whack-a-mole for 20 years. Every time a clever solution popped up, hey, let's just optimize the shape, a new, even worse problem would slam it back down. Sorry, you just roasted the crew.
It did feel that way for a long time. The general sentiment in the field was that general relativity might allow it mathematically, but quantum mechanics would always forbid it physically, a cosmic veto.
But, and this is where it gets really, really interesting in our stack of research. The entire tone of the research seems to have shifted. We are looking at a cluster of papers from the 2020s, specifically post-2021, and the mood is completely different. We seem to have entered a new frontier.
We absolutely have. And the shift in thinking is profound. For decades, the central dogma was warp drive equals negative energy. That was it. If you can't get negative energy, you can't have a warp drive. Full stop. The new wave of research is challenging that fundamental assumption.
This is the positive energy revolution.
Right. And it really started picking up steam around 2021 with a paper by a physicist named Eric Lentz at the University of Göttingen.
So what did Lentz do differently? Did he discover some new kind of exotic matter?
No, he found a new kind of geometry. He went right back to the original Einstein field equations, and he looked at a component called the shift vector.
The shift vector, that's the part of math that tells space which way to flow, so to speak.
Roughly, yes.
Yeah.
Alcubierre, in his original paper, used a very simple linear arrangement for this shift vector. It was a specific choice he made. Lentz realized that these equations are incredibly complex and can have many different families of solutions. So he tried using hyperbolic relations instead.
Hyperbolic sounds complicated, but in terms of the source, the stuff you need to build it, what does that change result in?
It results in a solution where the source of the gravity, what we call the stress energy tensor, looks like it's sourced by purely positive energy density.
Wait, pause right there. So no exotic matter, no negative energy, no fighting with the quantum bank.
That is the claim. Lentz proposed that this very specific space-time geometry could be created by completely conventional sources. Specifically, he talks about magnetized conducting plasma, arranged in a very particular way.
Plasma and magnets. I mean, that sounds buildable. We have plasma, we have magnets, we have fusion reactors that use both of those things right now.
In theory, yes, it's within the realm of known physics. The shape of the bubble is different, though. It's not the smooth, simple ring that we see in the Alcubierre Drive diagrams. Lentz describes it as a multi-lobed shell.
I'm looking at the visualization from his paper right now. It looks almost like a diamond lattice structure, like a cage surrounding the central region.
A lattice of what are called solitons. A soliton is a special kind of wave. It's a self-reinforcing wave packet that maintains its shape as it propagates. So Lentz argues that if you can create this diamond-like pattern of plasma solitons, you can bend space-time into a warp configuration without violating any of the known energy conditions.
That is a genuine game changer. If we don't need negative energy, the biggest and most fundamental stop sign in this whole field just vanish. But there has to be a catch, right?
There is always a catch, and the catch is that the energy amount is still enormous. To build a lens drive for a 100-meter ship, his initial calculations suggested you'd need to convert the total mass of roughly 10% of our sun into pure energy.
Okay, so we've traded impossible physics, which was negative energy, for impossible engineering, which is harnessing 10% of the sun.
That is progress in theoretical physics. Impossible engineering is just a matter of time and budget. Impossible physics is a hard stop from the universe. But there's also an ongoing debate about the math itself.
Right, I saw some of the counterpapers in our stack from authors like Santiago, Schuster, and Visser.
Yes. Physicists love to peer review. And these critics argue that Lenz might have made a subtle error in how he calculated the energy conditions. They argue that if you look at the drive not just from the perspective of someone on the ship, but from all possible reference frames, you can still find spots where the energy density goes negative.
So the ghost of negative energy might still be haunting the machine, just hiding in the corners.
It might be. But the door that Lenz opened is still hugely significant because it shifted the entire conversation. It forced everyone to go back and re-examine the fundamental equations. And that led to another major development by a pair of researchers, Bobrick and Martyr.
Their physical warp drives paper.
Yes. And this was a really clarifying moment for the field. Bobrick and Martyr took a step back and just asked, what is a warp drive, really? And they came up with a very simple definition. It's just a shell of material that moves inertially and encloses an interior region.
So any bubble of matter that separates the inside from the outside.
Exactly. And they showed that technically, a simple spherical shell of normal, positive mass matter is a warp drive. It creates the required geometry.
But they focused almost entirely on subluminal warp drives, slower than light. I have to ask, why would we want a warp drive if it doesn't go faster than light? Isn't the whole point to go fast?
Not necessarily. Remember that other amazing property we talked about, the free fall aspect?
Oh, right. No G-forces.
Bobrick and Martyr pointed out that a subluminal warp drive is the ultimate comfort ride. You could use it to accelerate to 99.9% the speed of light. In a normal rocket, that kind of acceleration would either take years and years or it would crush you into a fine paste. In a warp shell, you could get there quickly and you wouldn't feel a thing.
And it also helps solve the tyranny of the rocket equation.
Right.
You don't have to carry all that propellant.
To an extent, yes. You're not expelling propellant out the back to push you. You are manipulating the geometry around you. So it reframes the warp drive from being an FTL machine to being an interstellar ferry. Even if we never break the light barrier, this technology would still completely revolutionize travel just within our own solar system.
First-class travel to Mars in 2 days, 0 Gs the whole way. I would buy a ticket for that.
Exactly. But then just when we thought we were maybe settling for slow but comfortable, we get a paper from 2025 from a researcher named Kiao.
This one blew my mind when I read the abstract, the numbers. Well, let's get to the numbers in a second. First, what is Kiao's approach?
Kiao uses something called generalized gauge transformations.
Okay, that is a mouthful. We need to break that down.
In physics, we generally have different forces. Electromagnetism and gravity are usually treated as two separate things with separate rules. But Kiao is working in a theoretical framework that tries to build a bridge between them. A gauge transformation is usually just a mathematical tweak that doesn't change the physical reality. It's like resetting the 0 point on a voltmeter. But Kiao proposes a method where manipulating electromagnetic potentials actually results in a real change in space-time curvature.
So, using electricity and magnetism to directly bend space and time.
Effectively, yes. Compressing space at the front of your ship, which is positive curvature, and stretching it at the back, which is negative curvature, by using carefully manipulated electromagnetic fields.
And the number that made everyone jump out of their seats was the energy estimate. Remember, Fenning originally said 10 times the mass of the universe, but Enbernbruck got it down to a few suns.
Kiao estimates that to create a 20-meter bubble, which is big enough for a decent probe or maybe a small one-person ship, would require about 4.9 million joules.
4.9 million joules. That's, I mean, I had to look this up. That's the energy in a couple of kilograms of jet fuel. That's the energy of a small tactical missile. That is not a star.
It is a number you can actually comprehend. It's an amount of energy we can produce in a portable generator today.
That is a staggering, unbelievable drop from the mass of the universe all the way down to a generator.
Now, we have to be very, very careful here. This is extremely theoretical work. The engineering gap between the math says 4.9 million joules, and building a machine that can actually turn that energy into space-time curvature is still vast.
Right.
We don't know how to couple that energy to gravity efficiently. Just having a tank of gas doesn't mean you can go anywhere if you don't have an engine.
But the trend line here is incredible. It's a trajectory that makes you sit up and pay very close attention. The cost of entry, at least theoretically, is plummeting.
It suggests that we're refining our understanding of the problem. We're stripping away all the inefficiencies in the math that led to those crazy early numbers. And sometimes, discovery happens by accident. And we have to mention Harold Sonny White.
The Eagle Works lab at NASA. I love this story because developing a warp drive wasn't even the main goal of his experiment.
No, it wasn't. Sonny White was working on a project for DARPA, and he was studying these things called Casimir cavities, those tiny structures with the two plates we mentioned earlier that create negative energy. He was looking at them for potential energy generation purposes.
Just doing fundamental research, trying to understand the quantum vacuum?
Right. But when they analyzed the energy density distribution inside the special cavity using a very sophisticated numerical model,
It looked familiar.
the pattern matched the Alcubierre metric. They found what they described as a nanoscale warp bubble structure. Now, it wasn't moving, it wasn't a propulsion device, but the specific geometry of positive and negative energy regions was there, in the lab.
So it's a tiny, real-world proof of concept. It says, look, nature actually allows this shape to exist on its own.
Exactly. It's a microscopic breadcrumb on the trail. It tells us we aren't just chasing mathematical ghosts.
So we have the math getting better, the energy requirements dropping like a stone, and we have accidental discoveries in the lab. It really feels like we're on the precipice of something. But, and there's always a but with this topic, we have to talk about the elephant in the room. The elephant that might go back in time and step on its own grandfather.
Causality.
This is the headache that just never goes away. In general relativity, space and time are not separate. They are woven together into space-time. If you mess with space in this extreme way, you are going to mess with time.
You are. And this is the hardest pill for a lot of sci-fi fans to swallow. The math is pretty clear. If you can move through space faster than light, there's always a valid reference frame, another observer moving at a different speed who will see you as moving backwards in time.
So FTL is time travel. They aren't two separate technologies. They are the same package deal.
Mathematically, yes. If you can build an Alcubierre drive, you can build a time machine. You can create what physicists call closed time-like curves, or CTCs.
Let's just walk through how that would work simply. I have a warp drive. I fly to Proxima Centauri.
You fly there faster than light. In the reference frame of Earth, you arrive now, more or less, but then you turn around. If you perform a specific maneuver, you essentially switch your frame of reference by accelerating in a different direction. You can travel back towards Earth and arrive in your own past. You can arrive before you left.
And that's where you get all the paradoxes. The famous grandfather paradox. I go back in time and I stop my grandfather from ever meeting my grandmother. Then I'm never born, so I never built the time machine, so I never went back. So my grandparents meet after all.
That's a logical nightmare. Or you have the bootstrap paradox. You go back in time and you give yourself the plans for the warp drive. You then build it based on those plans.
So where did the idea for the warp drive actually come from? It has no origin. And a very recent paper from Shoshani and Snodgrass in 2024 actually modeled this explicitly. They showed how you could mathematically glue two warp drive metrics together to create a time loop.
They did. They proved that if the warp drive is physically possible, then the time machine is also mathematically sound.
So if we build this thing, do we just break history? Does the universe implode in a puff of logic?
Well, that's assuming history can be broken. This is where we get into what some call the defenses of reality. The most famous of these is Stephen Hawking's chronology protection conjecture.
Which is basically the universe's immune system saying, not in my house.
Pretty much.
Yeah.
Hawking argued that the fundamental laws of physics will always conspire to prevent CTCs from forming. For example, he suggested that as a time machine or a warp bubble, configured as 1, is about to close the loop on the timeline, the vacuum fluctuations would build up on its horizon.
Those virtual particles again.
Yes, they'd get caught in a feedback loop, circling around the time loop, gaining energy with each pass, until the energy density becomes infinite, and the machine is destroyed in a blast of radiation right at the moment it was about to violate causality. The universe self-destructs the mechanism to save the timeline.
So every time you try to turn on the return to yesterday setting, the engine just blows up.
That's the theory. There are also other arguments, like the generic condition. Maybe these solutions for time machines exist mathematically, but they're like a pencil balanced perfectly on its sharpest tip. It's possible in an equation, but in the real world, the slightest breeze, the slightest imperfection in the mass distribution makes it fall over. Nature might not allow the perfect, infinite precision needed to build a time machine.
There's also an alternative view I read about that I find really compelling. Maybe FTL itself is possible, but the specific geometry needed to turn around and come back to your own past is what's impossible.
Yes, this is sort of the safe compromise for the universe. It suggests that you can travel FTL to the future of a distant star, but you can never configure the return trip in such a way that you land in your own past. You remain causally isolated from your own history.
So we get the stars, but we don't get the DeLorean. We can colonize the galaxy, but we can't go back and fix our mistakes.
That feels like a very poetic and frankly a very likely outcome for physics, a one-way ticket to the future.
I want to pivot to one last implication before we wrap things up, because if we are thinking about this, if our physicists are writing these papers on plasma solitons and gravitational curvature, surely, if there's anyone else out there, they've already figured this out.
This is a fascinating and very new area of SETI, the search for extraterrestrial intelligence. For 60 years, SETI has been almost exclusively listening for radio signals, for beeps and boops.
Basically assuming that advanced aliens are using 20th century human technology.
Exactly. But now, researchers like Eric Lentz and a collaborator named Felton are asking a new question. What does a warp drive actually look like from the outside? If there is a galactic federation zooming around out there, they aren't using chemical rockets, they're using metric engineering.
So instead of listening for the radio shows, we should be looking for their exhaust, looking for the wake their ships leave in spacetime.
Technosignatures, exactly. If a ship is using something like a lens drive, that massive positive energy plasma structure, it would disturb spacetime in a very significant way. It might generate gravitational waves.
But these would be different from the ones that an observatory like LEGO detects.
Yes. LEGO is built to detect enormous cataclysmic events like two black holes colliding. A warp drive would be a much smaller, continuous source, and it would likely have a very specific high-frequency signature. We could, in theory, tune our detectors to listen for the steady hum of a distant warp engine.
Or what about Doppler shifts?
Right. If a ship is compressing space in front of it, any interstellar dust or gas particles it runs into would be hit with an incredible amount of energy. They would release high-energy radiation, like gamma rays. So we might see these strange moving streaks of gamma rays or specifically blue-shifted light that just don't make sense for any natural object.
So the search for warp drives isn't just about trying to build one for ourselves. It's about spotting the traffic that might already be out there.
Precisely. We are moving from listening for messages to looking for engines. And if we ever see the wake of a starship, we know instantly that it's possible.
That's a staggering thought. Just one confirmed detection would change everything. It would prove that the physics is solvable and the engineering is achievable.
It would be the ultimate proof of concept, handed to us by our galactic neighbors.
So let's try and summarize where we've been. We started with this beautiful dream of surfing space-time. We almost immediately hit a wall of negative energy that required 10 universes to power. Then we found a potential loophole with positive energy and plasma. We watched as theorists optimized the geometry and the energy requirements dropped from cosmic scales down to the energy in a fuel tank. And now we're starting to look for the wakes of other starships in the sky.
It means we are in the middle of a profound transition. We are moving from the fundamentally impossible phase of this research into the really, really hard engineering phase. We still don't know if we can actually build a warp drive. The challenges, causality, stability, controlling that much energy, they are all still monumental. But for the first time in a century, the laws of physics don't seem to be shouting, no.
They're not slamming the door in our face.
They're whispering, maybe, if you're clever enough, if you can truly master the geometry of space-time.
And that maybe is more than enough to keep us looking up. It's enough to keep the papers coming.
It certainly is. This stack is only going to get higher.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support.
And to our listeners, thank you for being part of this journey with us. If you enjoyed today's episode, be sure to subscribe and follow Stack Studios for more informative content. And support us in Patreon.
Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.